Alright guys, so this is lesson 1.1, and you'll find this lesson also in the materials section for this week. And I'm using Smart Notebook to display it, but if you open it up in your Google Slides, the links will work. So you just have to click on the link, it'll take you to these videos or problems. So I'm going to keep going, but these are here for extra resources. So we are discussing in Chapter 1, Unit 1, motion. So we're going to represent motion different ways, and we're going to start doing that here. So there's an image here of kind of a picture of a bird flying through the air, and this is like a stop motion picture, so every second that goes by you see where the bird has moved, and we're going to represent how that motion occurs and different things. And there's many different types of motion. We're going to start with straight line motion, so it's moving in a straight line in a certain direction, either horizontal or vertical. We'll get into projectile motion after that, which is an object moving in 2 dimensions under the influence of only gravity. And then we'll get into other more complicated types of motion like circular motion or rotational motion. But in all these things, all these different types of motions, the path that an object takes is called its trajectory. So we're going to start with motion diagrams. So this is I call them motion maps. So again, it's just displaying the object. Sorry, let me adjust this a little bit. There we go. The object, and every time you see a picture of that object, that represents some specific unit of time. So I'm putting little dots on things because we're going to use a model called the particle model, and it's easier to follow the dots than maybe the whole image of these objects. So from those pictures, you can see that you have 3 different objects: a skateboarder, a runner, and a car, and they are moving in different ways. So it tells you how they're moving here. Let's just kind of talk through why they are described that way. So for the person on the skateboard, they're going at a constant velocity. So the dot represents the object, and every time a particular unit or amount of time goes by, they put another dot. So we'll just say each dot represents 1 second of time. So the skateboarder moves that space in 1 second. So if this is 0 seconds when we're first start noticing and recording the motion, this would be 1 second, and 2 seconds, and 3 seconds. And as you can see, it looks like these are all equally spaced. So this person is moving a constant amount of space in a constant amount of time, which would be a constant speed. So you probably are familiar with the concept of speed. It's just how fast you move, and that is what's being displayed in that first image. The second image is a runner, and that runner is going faster. The reason why we can tell it's going faster, if you look at the spaces between the dots again, those spaces are getting bigger. So the velocity or speed is increasing, and it's covering more distance or more space as time goes by. And then finally, the car here, the last one, it's the opposite of the runner. So it starts out with a larger amount of space, and then that space gets smaller and smaller as time goes by. So that is that kind of idea. We can use these motion maps to do more complicated types of motion here. So we have a basketball, and we could use that as well. So I could put the dots at the center of the basketball, and you can see now the basketball is going through multiple dimensional motion. So it's moving up and down, and it's moving across, and we can kind of see what's happening as it goes through with these kind of motion maps. So let's just check to see if you understood what I was asking you. So in this one it says motion maps are made of 2 different cars, the red car on the left and the yellow car on the right, so car A and car B, and it says which one is going slower. So again, I like putting in the dots because I can kind of imagine that's seconds going by. And we're making a couple assumptions here. First off, we think that whatever way the car is facing is the way that it's moving. So I would imagine this car, the red car, is moving to the right, and I would say the yellow car is moving to the left. Again, it looks like they're all equally spaced dots, so if we're measuring sort of the distances between them, these lengths don't change very much. And same with car B, which is going to the left. So let me give you a chance to say which one you think is going slower. the correct answer is car A. So car A is going slower because it doesn't cover as much distance in a unit of time. So in 1 second, it only travels from here to here, where car B has a bigger section. So if we measure this section for B compared to the section A for A, A is smaller, which means it's going slower. All right. So we talked about drawing the dots. That's just what's called the particle model. So what we do is we draw a dot to represent the whole object. And the reason why we do this is to try to fix this. Sorry. There we go. We do this to try to make it uniform, so we can see what's going on. Try to move this down a little bit more. Sorry. There you go. Oh, not quite. I'll edit. I'm sorry. So the dots represent this whole car, and the way that we get away with this is just to simplify the motion. So instead of looking at an object as a big collection of particles that are all independently moving, which they can be in more complicated motions, different parts of objects move differently, but the way we're going to simplify it in the beginning here is we're just going to say everything is moving exactly the same way. So every particle in this car is moving the same way as that central dot that we concentrate all of our mass at. So we've discussed that in the previous slide, so I'm not going to spend too much time on it. Let's take a look at this one, and another check to make sure you understood what's going on. So again, every dot here represents a unit of time. There we go. And so this would be like 0 for A, 1, 2, 3, 4. I'm gonna let you count. I want to skip some. 5, 6, 7, 8 seconds here. And if I do the same thing for B, it'd be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like maybe I counted wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, I did it right. 0, 1, 2, 3, 4, 5, 6, 7, 8. Yep. So if we take a look at this, the one that I think they're closest together, or they're at almost the same spot, is here. And it takes 5 seconds for A to get there, and it takes 6 seconds for B to get there. So I would say that A is going faster. That is the correct one here, and it is. So one other thing that we need to do to represent motion properly is to establish basically what's called a frame of reference or a coordinate system. So a frame of reference is just what you're measuring in comparison to. So luckily in math class you've kind of learned frames of reference already when you've graphed different items. So this Cartesian coordinate system is what we will commonly use in physics. So you got the x and y axis, and positive and negative x, and positive and negative y. And those nicely line up with a lot of the situations that we have. So this is a really common way that we represent a frame of reference. So, so in this example, it says the origin of our frame of reference is at the post office. So I'm assuming that's the post office. And we would want to measure objects' locations or positions in reference to that post office. So if you look at this car, the car is positive 4 miles from the post office. So it's positive, which means to the right in this frame of reference. So positive is right. That's important. And then also, if we look at the opposite direction is left, which is negative. And this cow is at -5. So looking at those coordinate systems and that frame of reference, we can establish where things are located in reference to here. You have the power to select your frame of reference, so that is important and a powerful way to maybe simplify some problems later on. But for right now, we basically just use the standard x and y axis. Okay. Another thing that we can do with coordinate systems is we can measure kind of changes in position. So we can see where something starts. Maybe like this runner is starting at 0, and maybe they're going to run a race and they're going to finish at 50. We can also figure out where they're located, how far there is to go. So again, that coordinate system tells us kind of our frame of reference. It also tells us the amount. So in the previous one we were measuring in miles, and this one we're measuring in meters. So it's just making sure that we have established all of the factors that we use to describe Oops, I skipped back instead. One other thing we need to be aware of is time. We want to say where something's located at a certain point in time or how it's moving at a certain point in time. So for that, we just, again, these motion maps are helpful because every dot is representing a consistent amount of time. Sometimes, or in some cases, we will want to record the value for the entire motion of something. So if we had it start here at 0 and it moved to 8, we might want to incorporate all of those times, but other times we might just want to focus on like when something is happening. So maybe this car starts braking here, and we just want to focus from here to here. So we can start time, again, according to our problem, when it's appropriate at certain instances, and analyze the motion at that time accordingly. So one of the first ideas that we're going to talk about is change in position, which is also known as the displacement of an object. So change in is the Greek letter delta, which looks like a triangle. And change in is a very common type of operator that we'll measure the change in many things. So we can measure change in position. This is a horizontal position, so that's why it's called change in x. If it was rotated 90 degrees and it was going vertically, so if the object maybe was starting at this intersection and going along that red arrow, that would be change in y. We can measure the change in time, we can measure the change in temperature, so there's lots of different availability to measure change in various things. When you measure change in anything, it's always final minus initial. So you're always taking the final value and subtracting off the initial one. To help you with this, with change in, so let's say we wanted to measure the change in height that you had from when you were in kindergarten to your height that you are now. Okay, so if I'm kind of just drawing a quick little sketch of this, so if you were here and this is your stick figure when you were in kindergarten, and then you measured your height now, which one would be the final one, which one would be the initial one? So we're starting at the kindergarten age, so that's the initial, and the height at the end now, that would be the final. And we want to take the difference of those. And sometimes people accidentally switch these and they put initial minus final. If you did that in this case, you would have shrunk. So if I take, if this is, I don't know, 6 feet, and this looks like maybe it's a little less than half, so maybe 2 feet. It should be 6 minus 2. So we would see that you grew 4 feet. That's your change in height over that time period. If you did it in reverse, you would get a negative value here. So you didn't shrink. That's not your change in height going from kindergarten to current height. You didn't lose height, you gained height. So you make sure that it just makes sense logically. Sometimes you can lose values, so like if you slow down or move in a certain direction, you can have kind of a loss or a negative value. That's okay. But it should make sense. It's always going to be final minus initial. And so for this one, the final position is 150 here. The initial position is 50. The change in position would be 100 feet. And this is a positive value. One thing with position, again, if you don't write out the positive, it's okay. But if it is a negative position, so say it like started over here somewhere, you want to make sure you include those signs. So this was our frame of reference at 0. If you were over here, that would be left, and that would be negative. That would be some negative position. So make sure you do that. The positive and negative, again, tell you the direction. So this is just, it means it moves to the right. If we flip this over, we would definitely get a negative value because it would be going this way. So the final position would be 50. And the initial position would be 150. And that would be a minus, or a negative 100 feet. So that means that our object moved to the left, which, again, is definitely possible. It's just you want to make sure that you include direction, and you have to clearly establish, like, oh, this is my final in this one, and this is my initial in the second example. Okay. So, I think I went the wrong way. So change in time, it's kind of the same thing. So time interval change in time is just the time initially, so we start at 0, and the time final is when you stop. So it would be 6 minus 0, so this time interval is 6 seconds. You don't have to start at 0 time. Again, it's easier because then it's just whatever value you end up at. But if you started at 1, if you're measuring from 1 second to 6 seconds, that change in interval would be 5. Again, you can't have negative time, so you always have the bigger number minus the smaller number per time. Okay, so we're going to look at displacement and position and kind of changing time variables for this person, Emily here, who is on a bicycle ride. And we're going to find a coordinate system so that increasing x means moving east. So increasing x, I just want you to think of that as like positive. So if you're going in the positive direction, that's going east. If you're going in the negative direction, you're going west. So it describes Emily as 3 miles east of the water tower. That's her initial position. And then 30 minutes later, she is 2 miles west of the water tower. So we want to figure out what is her displacement during that half hour. So we're going to use the particle model. We're going to draw some dots. She's going to ride from east to west along the road. We're going to describe it. So if we look at a picture and we drew it out, if this is the dot for Emily, to start, so she is 3 meters to the east of the water tower. So the water tower here is at 0. She's at a positive 3. And she's gone from positive 3 all the way over to 2 miles west of the water tower. And we want to figure out what is that displacement. So the displacement would be the final minus the initial. So we would do the final position, which is negative 2. And she started at positive 3. So our displacement is a negative 5. The unit is miles, which means that she moved 5 miles to the left. And that is what we see here in this motion. So this arrow in the direction is pointing in the direction of our vector, our change in position. There are other ideas that we can measure. So this is displacement again. We could also measure distance. Distance is just the space between the two positions. So you don't worry about the arrow with distance. Distance is just like how many steps you go or how far you move. So it's not exactly the same. So distance versus displacement. Displacement is delta x and distance is just d. Alright, so we just went through that, so not a big deal. We'll keep it going. Alright, so let's try this one. So it says Maria is at a position of 23 meters. She undergoes a displacement of negative 50, and we want to figure out what is her position. So again, drawing a little sketch is important, so I'm going to just start with a number line. And I'm going to call that 0. And this is 0 meters. We're measuring in meters along this number line. And Maria is over here. I'm going to count by 25s. So if we say this is Maria, this dot is Maria, she's starting not at 25, sorry. We're starting at 23. So a little bit close to the 25, so it's a positive 23. And we're trying to figure out where does she finish. So we're looking for her final position, which is xf. Now, you might be confused because you're like, well, I don't know what to do. It tells you the displacement, so that's helpful. So we know it's negative 50, so she's moving to the left 50. And we're going to use that displacement equation. So the displacement is the change in position, delta x, so it's final minus initial. And if you plug in the values, we got negative 50 here equals the final position, which we don't know. That's our thing that we're searching for. And I have minus 23 for that. So we're going to solve this. So I'm going to take the 23 to the other side. If it's negative on the right side, it's positive on the left. So I'm going to add 23 to both sides. Doing a little bit of algebra here. So I get the final position would be negative 50 minus or negative 50 plus 23, which is a negative 27. So negative 27 meters is her final position, which is where she ends up here, and that's answer A. Okay. I'm going to pause there and stop the video because it's getting a little long, and I'll break it up into 2 parts. So I'll be back.